Okay, good afternoon. Let us start our lecture. So, in the last lecture, we talked about distributions. So we discussed about some continuous distributions, including uniform distribution, exponential distributions. All right. So now we talk about this normal distribution, which is a very popular or very common distribution. All right. So okay. So a random variable x, all right, which takes any values between minus infinity and infinity. That means any real numbers. All right. It's said to follow a normal distributions if the PDF is given by this form. The form is not important, but then it basically the PDF is, it looks like this. A cross section of a bell. All right. Just like this, with the center is symmetric about the value mu. Okay, so this is the x, while this is the f of x, the value of the density function. So the density is the highest at the point of x equal to the mu. All right, and then the spread out determined by this sigma. So we denote this normal distributions using the notation normal with two parameters. One is mu, the other is sigma square. I emphasize again, so a distribution, no matter which family that they come from, so there are some constants that determine the behavior of the distribution. So there are infinite number of normal distributions, and each one is identified by or characterized by two constants. One is mu, the other is sigma square. So you have to see the link between these two constants appear in the PDF and the expectation of variance, because we have ideas what we mean by expectation and the variance of a random variable. So we try to link up these two to the parameters of the distribution. So in this case, it turns out that the first one is the mean, while the second one is the variance. All right? Okay, so let's look at some of the properties about normal distribution. So the distribution has this, look like a bell, a cross-section of a bell, and it's like this. All right? So this graph is from normal with mean mu, 0 and standard deviation 1. All right. And the second property is obvious. The maximum point of the PDF occurs at the center when the x equal to mu. And the value, the maximum value of the PDF is 1 over square root 2 pi sigma. All right. You just substitute x equal to mu, then the exponential part is 0. So e to the power 0, so it's 1. So left with only this factor, 1 over square root 2 pi sigma. All right. So you can also see from here that the maximum value of the PDF depends on 1 over square root 2 pi sigma. So you can think of it, if sigma is big, then this quantity will be small. So in other words, if the variation is big, all right, then your PDF will be, the maximum of the PDF will be smaller. All right. So to draw the picture, it simply means that if you have a small sigma, all right, then this value is bigger than if I have a bigger variation. So big, this is for large sigma, while this one is for small sigma. So you can see that the maximum is smaller from determined by this part. All right. So it's very interesting that you look at the expression and then you can see some of the properties from the expression. So this is the maximum value of the PDF. It's equal to 1 over square root 2 pi sigma. So sigma big, then this quantity is small. But what does sigma big mean? So it means that the variation is big. All right, and then the normal curve, that means the PDF, has this property that it approach to the horizontal axis, all right, when x goes to infinity or x goes to negative infinity. So the tail part getting closer and closer to the x-axis. All right. Then, of course, no matter how you expand it, the area under the curve, that means under the PDF, should equal to 1. So in other words, it's just saying that from minus infinity to infinity, f of x dx, this is equal to 1. That means the area under the curve, under the PDF, should integrate equal to 1. This is true for all distribution. All right? So, then we can show that, although it's not that easy, but we can show that the expectation of x for x follow normal distribution, expectation of x equal to mu, and the variance of x equal to sigma squared. So it's a little bit more complicated when you do the integration, so we skip this part. We just say that it can be shown. So that means if you're interested, you go and show it, all right? But if you don't know, just look for the book or just quote the results, all right? But no harm just to try it out. It's not so straightforward. All right, so, okay, then how these different values of mu and sigma square affect the distribution. So sigma is sometimes considered as the scale parameter or the shape parameter. So the different sigma will give you different shape. But if sigma is fixed, then the shape will be the same. So in this case, these two normal distribution, each one has a variance equal to 1. All right? So they have the same shape. But the difference lies in the mean. So this is mean equals 0. All right? While this one is with mu equal to 2. So you can see that they are the same shape, except that the center is different. One is center at 0, the other is center at 2. Because the expectation of the first one is 0, while the expectation of the second one is 2. So now you can see that the mu basically is the location parameters. It tells you where the center of the distribution is. While the sigma tells you the shape or scale of the distribution. So this is another two distribution with the mean the same. That means they are at the center at 0. One has a variance equal to 1, while the other one has a sigma equal to 2. So you can see that the sigma equal to 2, that means there are larger variation. So it's like that. All right. Okay. Now this property eta is very, very useful. What we have here is try to what we call standardization. We try to link up this x, which follow normal 0 sigma square. Then I take a transformation z, right, minus the mean, divide by the standard deviation. This procedure is called standardization. Why call it standardization? Because once we do this transformation, then this expectation of z can be shown equal to 0. And variance of z, all right, is equal to 1. Okay, so this is considered as a standard or as a reference. All right, so the center at 0 and the variation is 1, or the standard deviation is 1. So how to obtain it? So we just minus the mean of the random variable and then divide by the standard deviation. All right. So this Z is called a standard normal distribution. So everything that can be referred to this standard normal distribution. And this is the PDF of the normal distribution. And what's the range? The range is, so when x is infinity, z is infinity. When x is minus infinity, z is also minus infinity. So this is the range. All right. You can, okay, so one of the importance is that there's so many normal distribution, but if we use this transformation, then every distribution or every normal distribution can be converted to a problem using the standard normal distribution. So therefore we just need one table that will tell us how the standard normal behaves, then we can compute whatever we want. Of course, if you have a graphic calculator or programmable calculator or computer, it may do the job. But the idea is important. Here, if I want to compute, all right, a random variable x which follow a normal distribution. X follow a normal distribution. Then I ask, what is the probability of x between x1, little x1 and x2? Now, by now you should know the way that we present the probability statement. The capital letter x represents a random variable. The little x, the lowercase x with a subscript 1 is just a number. x2 also is a number. So we are talking about this random variables lies between two values. So you can think of it like this. So suppose this is x and a normal mu sigma square, and this is x1, this is x2. So we are asking, what is the chance that the random variable lies between x1 and x2? So it's equivalent to this area. All right? So what we do is to do standardization. You do standardization by on x, the random variable x, so you have to minus the mean and then divide by the standard deviation. Mean, mu, and standard deviation sigma are constants. All right, so I just do the thing, do this one. So x1 less than x2x. So I minus mu divided by sigma. So is this correct? Hey, it's not fair. You do something to the middle term. In fact, there are two inequalities here. All right? One is x1 less than capital X. The other one is capital X less than x2. So you cannot just do something for one of the inequality, one side of the inequality. Whatever you do, you have to do on both sides. So if you subtract something, you subtract from the right-hand side of the inequality and the left-hand side of the inequality. So you have to minus mu for all this. So it should be minus mu. All right. Does it matter whether mu is positive or negative? It doesn't matter. Adding a positive number or negative number will not reverse the inequality sign. But divide by sigma. Every expression have to divide by the sigma. Will it reverse the inequality? Only when sigma is negative. But here sigma is positive. The standard deviation is positive. So we don't have to worry about reverse the inequality. But always remember, you are not working on an equation. You don't work on an equal sign. So if you work on inequalities, you multiply a negative number, all right? For example, it's true that 3 is less than 5, right? Then I multiply both sides by minus 1. So it becomes minus 3 and minus 5. So you cannot say that minus 3 is less than minus 5. Is it correct? No, minus 5 is less than minus 3. So you have to reverse the inequality. So when you multiply a negative number to the inequality, remember you have to reverse the inequality. All right, so this is equivalent to the probability of z less than z1 and z2. All right. So, for example, I have x, which is normal with mean 50 and standard deviation 10. By the way, I think, I don't know, sometimes I forgot to change. It's not 102, but 10 raised to power 2. All right, so it's 10 squared. So that standard deviation is 10. I want to compute the probability of x between 45 and 62. So, take out your calculator and then you can work it out. But here, I want to convert this to a statement involve a standard normal random variable. So, I just have to minus the mean for this side and divide by 10. So I do the same thing. This one becomes x minus 50 divided by 10. And this one I call it z because it's a standard normal now. And similar for this one. So it's equivalent to z between minus 0.5 and 1.2. All right? Quite straightforward. But you have to pay attention. So this last statement that you saw here, you see here, is that this standard normal random variable between minus 0.5 and 1.2. Now, in fact, this minus 0.5 you can interpret as we are asking what is the chance that this standard normal random variable is 0.5 standard deviations below the mean. All right? So what I'm saying is that this is standard normal. So the chance between minus 0.5 and 1.2. All right? 1.2. So what is the probability lies within this? So this number is minus 0.5. But for standard normal, it also means that it is 0.5 standard deviation. Half of the standard deviation. This number, right, is equal to 1 times, is equal to mu, which is 0, minus how many standard deviation? Minus, this is the standard deviation, this is the mean. So it is 1.5 of the standard deviation below, 0.5, sorry, not 1.5, 0.5. It's 0.5 standard deviation below, because it's minus. Okay, this is the center. So you have below it, so it's minus, it's negative. So it is interpret as it is half of the standard deviation below the mean. Then how about this 1.2? 1.2, I can write it as 0 plus 1.2 times 1. All right? In fact, now it becomes, okay, this 1.2 is interpreted as 1.2 standard deviation above the mean, bigger than the mean, 0. All right? So this is a way to look at it. All right? So so many random variables that follow different normal distribution. If we want to standardize it, we compare. How to compare? Everyone convert to a standard normal. So in this case, this probability of x between 45 and 60 is equivalent to saying that what's the chance that x lies half standard deviation below the mean and 1.2 standard deviation above the mean. The mean is 0 for standard normal distribution. All right. So so it's equivalent to z less than 1.2 minus z less than 0.05. All right. So I want this probability. So it's equal to all this. All right. less than 1.2, and then subtract this part. So the difference will be the one that we want. By the way, if you want to look at how to get the probability, it's better to draw the picture like this. So the question is, we are asked to find the probability of Z between minus 0.5 and 1.2. So you write down that, and then you convert it to the difference of 2 CDF. All right, Z less than 1.2 minus, okay, so basically it is F 1.2 minus F 0.05. All right, F is the CDF. F is the probability of X less than X. So this is our F of X, the CDF. That's the notation that we usually use. Okay, so this one is help you to practice the properties of probability and normal distribution. First of all, this one less than 1.2, so it's equivalent to 1 minus Z greater or equal to 1.2. This is just a complement event of this one. So it's 1 minus the probability of the complement event. And then this one and this one, how come they're the same? All right. Let me repeat. This event, are they the same? Are they the same? Z less than minus 0.5 and Z greater than 0.5, are they the same? No. Different events. But, Z less than minus 0.5 is this part. Z greater than 0.5 is this part. Of course, they're not the same. But the probability of this one is equal to the probability of this one. Why? Because the standard normal is symmetric about the center. And what's the center for standard normal? Is 0. All right, for this one, all right, don't write down probability of X less than 62 is the same as probability of X greater than, okay, all right, don't write it like that because the center, X does not have a center at 0, so you cannot convert it. This one, all right, because it's symmetric about 0. So that less than 0.5, that means this part, all right, this probability is the same as this probability because it's symmetrical. If you don't get it, put a mirror there and see whether this part is the mirror image of that. All right? Well, this is not, because the mirror that you put is not at 0, but at the center, which is 50. All right? So it's not. Okay. Now why I have to do all this? Because in case you don't have your graphic calculator or a very powerful computer, then you need to rely on a table, a statistical table, not the usual table. It's a table. So the table will give you something about the normal distribution. So it's like this. So this is the probability of a standard normal greater or equal to 1.2, and this is the probability of Z greater than 0.5. All right? Hey, which one has a bigger probability? These two. This one, Z greater than 0.5, and Z greater than 1.2. Which one has a bigger probability? Ask yourself, which one is a subset? If this is true, this is automatically true. When this is true, okay. When this is true, when you have something that is bigger than 0.5, okay, 0.5 is here, right? 0.5. So So the probability of greater than 0.5 means this probability. So 1.2 is here. So the probability, because 1.2 is further away, so the probability will be smaller. All right? Okay. Okay. Here is the. Okay, unfortunately, there's no unique way. This is a table. I can only tell you, okay, a certain value of z, and what is the chance that greater than that value. So whenever you see a table, what we call statistics table, please read the instruction or the legend. In this case, all the numbers shown here are the upper tail, or the probability of the random variable greater or equal to that particular value. Okay, so there are two things here. One is the upper tail probability. That means 1 minus the CDF. All right. The other one is the little z, the constant. All right. So how to read it? So basically, if you design a table, tell people how to use this table. So you need to present two things. One is the probability, or cumulative probability, or the upper tail probability. The other one is the x. So given x, give an x, then you can compute the probability of a standard normal bigger than that value. So it is here. So you can see that. Okay, so this part and this part are related to the z value. All right, how to use it? So suppose I want to know what is the chance that a standard normal bigger than 1. So 1, this is 1. These columns tells you the second decimal place. So 1 is 1.0. So this is the probability. 0.1587 is the probability of a standard normal greater or equal to 1. All right? How about 0.5, greater than 0.5? 0.5 here. So it's 0.50, so it's this number. 0.3085. So this is 1.2. So then, how about probability of a standard normal greater than 1.23? 1.23. So, this is 1.2. This is 1.20. This is 1.2, adding this one. This is the second decimal place of the z. So this is 1.21, 1.22, 1.23. All right? Oh. So this is 1.23, this value. So that is the probability of a standard normal greater than 1.23. Okay. Then how about probability of z greater than 1.234? 1.234. Hey, no third decimal place there. All right, then what to do? Okay, so someone suggests to take the closest one. So 1.234 is somewhere between 1.23 and 1.24. So you take the closest, so maybe you take 1.23. Or you take the average of the two. Which two? 1.23, the value that you see under 1.23, and the value is go to 1.24. Take the average. Which one is better? Average is better in this case. I've even a better approximation. Wrong with the question, no, nothing wrong. I asked what is the probability of z greater than 1.234. So the third option is we call it linear interpolation. It's just basically a weighted average of these two numbers, under 1.3 and 1.24. It's closer to 1.23 because 1.234 is closer to 1.23. So we put more weights to that value that you obtain from 1.23. Right? So you don't know how to do linear interpolation? Fine. You don't know to take the average? Fine. So I accept the most simple one. Take the nearest one. All right. But remember, this is only an approximation. The idea is it's like this. Okay, before I close this one, let me ask you. I want to have a z, find me the little z, such that the chance of the standard normal greater than this value is 5%. I want to find a value such the standard normal greater than that value is 0.05. Is this the answer? No. Just now we try to fix the z. These are the possible z values. All right, we combine them and then get the z value. All right, the first decimal place and second decimal place. This is the probability. So now I want the probability. I want to find the z such that the probability greater than it is 5%, 0.05. Is this 0.05? No, it's 0.1. So, here and here. These two numbers. These are the probability. So, what is the z value? Give me 0.0505. So that one is 1.64. Chance of z greater than 1.64 is 0.0505. It's not my answer yet. The next one is 1.65. Then the chance greater than it is 0.0495. Okay, so take either one now. Closest one. Somehow this is no closest, this is exactly in the center. Right? 0.05 is equal distance from 0.0505 and 0.0495. So naturally you take the average out. So the answer is 1.645. All right? But I just give roughly idea what the value is. So the answer is 1.645. But let's say 10%. 10%. Then where's 10%? So 0.1. Where's 0.1? Now, this one, this two, right? So this is the probability. So when it's greater than 1.28, it is about 10%. And greater than 1.29, it is 0.0985. It's very close to 1.28. So let's take 1.28, right? Okay. Now, okay, so that's how you get the answer. This table basically is like this. Think of it. We have this is the PDF, right? So we can work out the probability, this area, all right? So for any possible z value, you can work out this probability by doing the integration. But unfortunately, it's not easy to do the integration. So now, sorry, I cannot give you, for any z, I give you the corresponding CDF. But I can give you, I divide this real line into, I get some points of it. So what are the points that in the statistical table that give you? So they give you, for example, 0. The next one is 0.1, 0.2, and so on. All right? So basically, it gives you 0, 0.1. So they give you the corresponding probability. All right? So it does not give you every possible z value. It only gives you certain z value. But they are not so different. All right? So start from 0, 0.01. I only have two decimal places. Two decimal places. All right? So 0.01, 0.02, 0.03, and so on. So after you reach 0.09, then the next one is 0.10, and so on. All right? So, of course, if you go back to, all right, this is the table, right? So, ideally, I continue to input here. So this is 0.0, this number is the probability of z greater than 0.09. So the next one should be 0.1, then 0.11, 0.12. So I can continue to write it. Right? I need a very long piece of paper. So why don't I cut it and then paste it under? So that's why I have the second line, second row here. Right? So that's how you construct a table. You understand? All right? So basically this table have only z and the probability of the random variable z greater than the lead to z. That's it. 2 rows. But I cut it and paste it under the row, so one follow the other. So that's how we have this table. All right. So I think I have discussed enough of all this. So let's move on. All right. So in this example, so we have this x follow a normal with mean 3 and 0.5 as the standard deviation. So ask what is the probability less than 2.3. So basically you have to do two things. If you don't have the calculator or computer to do it for you, convert it to standard normal. X less than 2.3, how many standard deviation? All right. This one, 2.3 is less than the mean. So it's equivalent to how many standard deviation below the mean. All right, so we all convert it, so you can see that x less than 2.3 is the same as a standard normal less than 1, is 1.4 standard deviation below the mean. So remember the table that I just shown you do not have negative number. What to do? Yeah, calculator can tell you. But if you understand that or you know that standard normal is symmetric. So this saying that standard normal less than minus 1.5. This probability is the same as greater than 1.4. All right? So that is given in the statistics tables. All right. So why I have to know all this? I have a calculator. I spent a few $100 to get my graphic calculator, right? The point is, can your calculator get the probability of that less than a constant, which I did not specify, less than 8? What's the probability? I don't know, right? So my point is, you have to understand the behavior of the normal distribution or standard normal distribution. All right. So in that case, you are able to compute even without a graphic calculator. All right, so the others are similar, so I can skip. All right. For Excel, just in case, this is not for exam. All right, you will not be asked to what command, how to use it. It's for you to compute. All right, it's a very powerful graphic calculator. All right, so use Excel. The command is normal.dst. All right. And then you specify 4 arguments. It's always like that. So the first argument is about the value. So suppose we want to find x, or for a given x, we want to find, let's say, x less than 8 or less than 10, for example. Less than this value, 10. So what is this probability? If x follow a normal distribution. So this x will be 10. Suppose the random variable follows standard normal. With 5 square. Variance is 5 square. All right. So then in this case, the mean will be 0, and this one will be 5. Remember, it's the standard deviation. In the notes, I always present it as the variance. Usually I just write it as something square. So you know that the standard deviation is just that number. So it's 5 square is the variance. So standard deviation is 5. All right. So, this one is is 10 square, not 102. Please correct it. It's 10 square. All right. Okay. So mean and standard deviation. True means that you are working on the cumulative probability. All right. If false, that means that you are working on the density function. All right. The density function. All right, so this is just another example. And for standard normal, you can forget about it. This one is good enough. It just has a function that works for standard normal. That means understood that the mean is 0 and the standard deviation is 1. So you just put 0 here and put 1 here, then you get what you want. All right? Okay. Now, inverse probability. All right. That is, what is this one? This one simply, okay, we can say that it gives you the quantile. It's try to find this value such that it's equal to something. For example, 0.06. Find a number A, a value A, such that the probability of the random variable X, which is normal with mean mu and sigma square, less than this number A with probability 0.06. So this is the probability, and X follow normal, let's say 0, 10 square, then this will be the mean, and this will be the standard deviation. And then that will give you the value A. Again, this is wrong. Please, it's 7 square. All right? 7 square, not 72. Yeah. Okay, so it means that if you have a mean 74 and standard deviation 7, all right, center is 74, so the chance that, okay, you want it to be, get a point such that the probability less than this point, this probability is 88%. So what is this point? This turn out to be 82.225. 82.225. All right, so that's what it means. All right, so this is, again, with the dot S dot, that will give you the standard normal equivalent. All right. All right. So let's look at some example. So now we know that once we write down the probability statement, we're able to compute the probability. All right. Okay, so let's say we have a common test. Average grade is 74 and standard deviation is 7. So if 12% of the class are given A's and the grades are curved to follow normal distribution, all right, then what is the lowest possible A? The grade, I mean the marks, or what is it? Can it be 74? If I set the lowest possible cutoff point is 74, those who are above 74 then will get A. Then what's the percentage of A? Huh? Is it obvious? What is this probability? No calculator, no computer, nothing. What is probability? X greater than 74. It's the mean is 74, right? So I ask you, what is the probability of X greater than the mean while X follow a normal with mean mu sigma square? Oh, mean. What is this? Half, 0.5. The question asked you is that, okay, find me the value, all right, such that the probability of greater than it is 12%. So that's what we are asked to find. Find this value, A, all right, such that it's greater than this value only 12% of the time. The lowest possible value of A, of course, right? So we try to get this mark. So this is what we are supposed to find. We're supposed to find x, the little x, such that we basically solve the equation. This is the unknown. Do we know anything about this capital X? It's normal. It's a random variable. And we know that it's normal with mean 74. And what is the standard deviation? 7. So it's like that. All right? So, solving this equation. So we go and look for this. I standardize it. All right, minus the mean divided by the standard deviation. And it's equal to 0.12. So now I go to look at my statistics table or your graphic calculator or using Excel. So it gives me the value roughly is 1.175. Here I use the most crude way. Get the table. I don't have calculator. I get the table and then I do I call it linear interpolation. But you can just try to take the nearest value, or close enough to give you 0.12. All right. Okay. So all right. So 0.12, right? We want 0.12. We want the p-value to be the probability to be 0.12. So it's between these two numbers. Oh, wow! Luckily, it is symmetrical. 0.12 is in the middle of these two. So it is 1.17 and 1.18. So it's the center in between 1.17 and 1.18. So I take 1.175. All right? Okay. So now this is the value. All right. So we work out x equal to 82.225. So the lowest possible A is 83. If you got 82.5, sorry, we don't have 82.5. It's marked integer, so 83. If you got one mark less, 82 is less than this number. So I will not give A for this. All right. So the moral of the story, work harder. You don't want to be on the boundary, on the other side of the boundary. All right. So if you got 90, you got A. Right. You got 82, too bad. All right. So I just want to highlight this one. So this saying that for a standard normal greater than 1.175, this means that it is 1.175 standard deviation above the mean. The probability is 0.12. So if my x is normal with mean 74 and standard deviation 7, then this is equivalent to x greater than 82.225. This random variable x greater than 82.225 is the same as saying that it is 1.175 standard deviation above the mean, because the standard deviation is 7 and the mean is 74. So you have to take this consider and then convert it to 82.225. All right. Linear interpolation. So you can see that here. So this number is in between these two numbers. 0.12 is between 0.121 and 0.119. All right. So this is corresponding to 1.17. The z is equal to 1.17. This corresponding to z equal to 1.18. All right. So in other words, what I'm saying is that, all right, okay, I enlarge it. So this is 1.17. This is 1.18. All right. So this probability is 0.119, and this probability is 0.121. And I want somewhere in between. I want the probability is somewhere in between these two values. So it's I want 0.12. So in this case, it's somewhere in between. So I take the average. All right. In fact, this is the formula. It's a ratio thing, basically. All right. So it's saying that, okay, now this part, this is the value that I'm looking at. So A minus 1.17, and then compare with this whole thing. That means I want to know this part, all right, relative to the whole thing, the difference here. Then I divide this region into this part as well as the whole thing. So it's 0.12 minus 0.121. All right. This is corresponding to A. These are the probabilities. All right. So this corresponding to this, and this corresponding to this. Anyway, this is not important. So if you don't know how to do it, but this is just a ratio thing. All right. A ratio is a very useful technique. So just take the average or take the nearest one. So that's how I got 1.175. But in fact, because of the special numbers here, it just takes the average. Okay, another example, referring to the previous one, I want to find the 60th percentile. Now, what does 60th percentile mean? 60th percentile means that you are looking for a value, let me call it x60, such that the probability is 60%. That means you want to find a value. Find this value. I call it x60, such that the chance less than it is 60% or 0.6. If you are in the 10th percentile of the test marks, no good, because you are only better than 10% of your fellow students. If you are 95 percentile, which means that you have a marks which better or larger than 95% of your cohort, so you are good. All right, so that's we interpret as for this percentile. So we are looking for the 60th percentile. So that means we want to find this x such that it's equal to 0.6. So we standardize it. It's equivalent to finding a value. If you want this to be 0.6 standard deviation above the mean, then it's the same as looking for a value which is 0.2533 in a standard normal. So convert it, it means that it's 75.77. So in other words, for this class, if you score a number, all right, above 75.77, then you are on the upper, it's better than a 60th percentile. All right. Okay. So, this one is interesting. Here, no use for your calculator. Mu is not given. Okay, so we have this machines to fill up the packets of sugar. It's supposed to be 500 grams. A machine has variation, so it fill up the package. Sometimes it is more, sometimes it's less. All right, but we expect it should hit 500 grams. Okay, suppose now we don't know what is the mean of this amount that packed into one package. All right, so suppose only 2% of the packets contain less than 500 grams. What does that mean? It means that this is the amount. This X is the amount of sugar, all right? It follows certain distribution, and we know that this is 500, all right? And only 2% of the packets contain less than 500 grams. All right, so this probability is 2%. right? Hey, so if, like I think you drink soft drink, right? Like the bottle, we can see the bottle, all right? So the machine tries to fill up the soft drink to a bottle. So if the bottle says 1.5 liter, so if you are the technician who set the machine, will you set the mean equal to 1.5? 1.5 liter. Well, if you set that, you'll fire it immediately. You set mean equal 1.5. That means half of the bottle will be below what you set, right? So you must set something different. All right? So this is what we are trying to look for. I want to set at mu, such that only 2%, in fact 2% may be still too high. All right? 1 out of 50 of them will get will be shortchanged. All right? I expect to get 500 grams, and then you give me a packet of sugar that has less than 500 grams. All right? But this is the number that we set. So how should I set my machine? So that is, I need to find the mu. All right? So it's different from the first two examples that we discussed. So now I have this equation. I want to find the chance x less than 500 with 2% chance. Hey, where's the unknown? You say equation, where's the unknown? Oh, the unknown is hidden. Hidden where? Hidden here. So I convert it to a standard normal by minus the mean divided by the standard deviation. Minus the mean divided, we know the standard deviation is 4, so I replace it by 4. So now the left-hand side becomes a standard normal. The right-hand side involves some unknown. The unknown is mu. So it's it is 500 minus mu over 4. All right? So now I ask myself, what is the value from standard normal? That less than that number is only 2%. So it works out that this number, I want this standard normal, this number, so that this is 2%. I don't have the table, but I have this table. I work out this number, 2.0537, greater than it is 2%. Because it's symmetric for standard normal, it's symmetric about 0. So this also says that probability of z less than minus 2.0537, that means this one, minus 2.0537, is also equal to 2%. So, compare this one and this one, right? In fact, this is how I set up the equation. These two, I say probability of z greater than this expression is 2%. On the other hand, I also know that from the table or from your calculator, you know that probability of z greater than greater than 2.0537, all right, is 2%. Is 2%. So these two numbers must be the same, right? So this is the equation. Solve this equation, we find that mu equal to 508.2. So you need to set your machine to dispose on average 508.2. So sometimes it's even more, sometimes even less. But we expect only 2% of those packets of sugar will have among less than 500 grams. All right. Um, 508. So as a consumer, I expect 500, but on average I got 8 grams more. 8 grams means how many percent? It's almost 2%. 1 point. So a lot. So if you're the company, so what to do? I check a bit, not 508. How about 505? What's the consequences if I shift to 505? Then you have more of the percentage of below 500 will be more. And that's no good. So what to do? what to do. How to make the mu smaller such that the percentage of less than 500. Yeah, decrease the variation. Think of it like this. This is 508.2, all right? The mean, the standard deviation is 4. So this is 500 and this is 2%, all right? So that's the problem. So now I don't want to give so much. So what to do? I want to shift my mean, all right? But if you think of it, if I shift the whole thing, I change from mean from 508.2 to 505. So basically I shift this part, shift the whole distribution. Then the probability increase less than 500. So it's no good. So I cannot just shift the mean. I remember there are two quantities that affect the distribution. So I changed my sigma. Instead of 4, so maybe change it to 2. Then what will it look like if I change it to 2? So it will, if mean is 508, if I change sigma to 2, then it will be, oh, I'm sorry, I couldn't draw it. So it's more concentrated around the mean. So now it's peak, and then, spike up, and then I also shift it. So in that case, my probability of less than 500 will be smaller. Will be if not smaller, but then that's a possibility that you can have satisfied that I don't give so much. All right? So I set my mean, which is smaller than 508. At the same time, if I can reduce my variation. So, how to reduce the variation? So if you can adjust it, try to adjust it. If no, get a better machine. Right? Usually it's the cheap one that will give you, right? Handphone, right? Well, I can have how many megapixel picture, right? You may pay more. So the same thing, if you want to be more precise, then usually it may cost you more. All right. So, but that's how you look at the problem. Okay. I think I skipped question 4, example 4. It basically, this is a type that, all right? The whole question, do you see any numbers? No numbers. Basically, I ask you a probability. A probability of what? A probability of the random variable lies within one standard deviation of the mean. Okay. X follow mu sigma square, and ask probability of X within one standard deviation of the mean. So X between mu minus sigma and mu plus sigma. All right, that's what. So I take out my graphic calculator. How to calculate this probability? What is mu? Sorry, I don't know. What is sigma? I don't know. But to calculate this probability, you don't need to know mu and sigma. Why? Standardize it. So this is equivalent to X minus mu over sigma, and this becomes 1, and this becomes minus 1. And this is the standard normal. So now it's equivalent to a standard normal random variable between 1 and minus 1. So that's it. All right? Okay? So it's true for any normal distribution. It's here, all right? So you can work out the probability is 0.6826. And these are very common. Z between one standard deviation is about 0.6826. Between 2 is roughly about 0.955 probability. All right? And how about 3? This is already 0.95. So for 3, I also give 3, right? 0.9974. So it's quite big. So in other words, if your distribution is a normal distribution, then we believe that the chance that your random variable lies within 3 standard deviation from the mean. That means lie within 3 standard deviation above the mean and 3 standard deviation below the mean, lie within this range. The probability is 0.9974. So it's quite big. So it's very difficult to see something outside that range, right? Because the probability is very small. Okay, so example 5. So we'll reject the components if it falls outside the specification. The specification is 1.5 plus D and 1.5 minus D. So this is the specification, all right? And we also know that the measurement is normally distributed. So that means X is normally distributed. X is the measurements of, or the measurement of the item of the component, which is 1.5 and 0.2. All right. So determine the D such that the specification covers 95% of the measurements. All right. So I want to find a D such that all the components, 95% of them will fall within this specification, and 5% is, do not match or do not meet the specification. So, so this is the question. Find D such that the probability of the measurements lies between this is 95%. So how to do it? So we know that X follow normal distribution with mean 1.5 and standard deviation 2. What is the standard deviation? 0.2. 0.2. Right, 0.2 square. All right. So what we do is just standardize it and look for how many. Look for these 2 values. All right. Okay. This is D over 0.2. This is minus D over 0.2. We are looking at this probability. What can we say about these 2 probabilities? They're the same, right? It's symmetric. So the same. So what I need is to compute this probability. All right? Now, in order this to be 0.95, then what is this probability? These 2 parts add up to 5%. So each one, because they're equal, so each one is 2.5%. So I want to find D such that a standard normal greater than D over 0.2 is equal to 2.5%. All right. We can do all this because we are working on a standard normal random variable which is symmetric about 0. So now the expression is that between D over 0.2 and minus D over 0.2, such that the probability is 95%. So outside it is 5%, and I put equal. They are equal because it's symmetric about 0. So we work out. So yeah, this is what I mean, 2.5%. And this value is 1.96. All right, so D over 0.2 is 1.96. So D is equal to 0.392. So in other words, it is 1.5 plus 0.392 and 1.5 minus 0.392. The probability of this one is equal to 95%. All right, so that's what it means. All right. Okay. Normal approximation to binomial. Remember we when we discuss about Poisson, Poisson also can be used to approximate a binomial distribution. Okay, so if x follow a binomial with NP, if n is big, all right, and p is small, big, n is big, and p is small, and then x can be approximately follow a Poisson with parameter NP. So here we can also approximate by the mean NP and NP 1 minus P. Put approximate. And again, it is n large. Usually, as a rule of thumb, is n bigger than 1. NP bigger than 5, or n times minus p bigger than 5. It's not so strict, but then this simply means that n has to be big and p has to be small. All right. But, sorry, not p. P small, then better use Poisson. All right. When p approach half, then we use the normal approximation. Then obviously you have this question, which one should I use, Poisson approximation or normal approximation? Now, normal distribution is symmetric. So think of it, if your p is very small, if you go back to look at the graph that I showed you, when p is small or very big for binomial distribution, it's very skewed. Think of it, the chance of success is very small. So therefore, majority of the outcome will be very small. The number of successes will be very small. But if p is close to 1, then the number of successes will be very big. All right? So it's skewed. But while for normal distribution it's symmetric, that's why when p approach to half, which is quite symmetric for binomial distribution, then the approximation will be good. So this is one of the criteria to decide whether you should use Poisson or use normal approximation. So if it's symmetric, the binomial is symmetric, that means it's around maybe 0.5, the p is around 0.5 or 0.4, 0.6 or even 0.35, then maybe still the approximation is okay. But if p is equal to 0.00001, then don't use normal approximation. But of course, if it satisfies NP greater than 5, then maybe okay. All right. Not only that, n times 1 minus p also have to be bigger than 5. All right, so this is a graph to show that. And we have this theorem. This theorem basically is writing down what I just said. If x is binomial with NP, then x can be approximate, follow with mean NP and variance NP 1 minus p. Right? So this is n minus expectation of x divided by the square root of the variance of x. This is the expectation of x. This is the variance of x from normal distribution. Because if x is normal, then this is equal to NP and variance of x equal to NP times 1 minus p. All right? Q here is minus p. Q is 1 minus p. Okay, so here is example. I have x follow binomial with with n15 and probability is 0.4. So I multiply the two. All right. So this is equal to 2 over 5. So 6, right? Which is bigger than 5. I also check, but this is obvious. Check this one. So this one turned out to be 9, also bigger than 5. Therefore, I feel comfortable to use the normal approximation. But of course, you don't have to use normal approximation. It's just to illustrate how the idea flows. All right? So, probability x equal to 4 is equal to 0.1268. Then, if x is approximate by normal with mean 6 and variance is NPQ. So it's 0.36. All right. Then what is probability of x equal to 4? Is it 0? Hey, continuous distribution is 0. X takes certain value is 0, right? If you are not confused, either you understand it or you really don't know what's happening. Let me ask again. X is binomial with n 15 and p, probability of success for one trial is 0.4. So I want to compute for x equal to 4, so I can compute it easily. But if I use this normal approximation, so we can approximate it, then it follows approximate normal distribution with mean equal to 4 and variance equal to 0.36. It is n times p times q times 1 minus p. All right, 0.36. Then, based on the normal distribution, what is the probability of x equal to 4? I remember I mentioned it for continuous distribution. X equal to a certain value, the probability is 0. Then is the answer 0? So that leads to something called continuity correction. All right, 0, 1, 2, 3, 4, for example. All right. So in fact, when we say x equal to 4, it means that it is x between 3.5 and 4.5. That's what it means. So when you say x equal to 4, when x is discrete, fine. But then when you try to use continuous to approximate it, then it means that x is between 3.5. Right? You are looking at this probability, right? So when you have a continuous approximation, it lies between these two lines, which is 3.5 and 4.5. So it's equivalent to x between 3.5 and 4.5. All right? So, okay, here it is. So 3.5 and 4.5. So the rest is just normal how to calculate the normal distribution. Now let me ask you, how about probability of x less or equal to 4? So if I approximate I'm going to use normal approximation. So this one, can I just say that it is 4? Or I have changed it to this one? Or this one? Which one? So you are in doubt. And look at this one. Let's say, all right, 0, 1, okay. 0, 1, 2, 3. Okay, so this is 4. Less or equal to 4. So that means all this. So where is the boundary? The boundary is here. This 4 is in the center. So this is 4.5. So this equivalent to this. All right? This equivalent to this. And how about this? So 4, 5, 6, 7. So now it's greater than 4. So including everyone, so including this small little part. So this will be equivalent to x greater or equal to 3.5. Am I right? You just count. X greater than 4, greater or equal to 4. So that means it's x equal 4, x equal 5, and x equal 6, and so on. But for x equal to 4, it means that x falls between 3.5 and 4.5. So the boundary is at 3.5 for this. All right. So here is you see? In fact, you don't have to write down all. If you understand the mechanism to generate the continuity correction, it's quite straightforward. So here you can see that, for example, I want to have x between is greater than a, but not including a. So you can think of it. So this is the a, and of course, there's something in between, and this is the B. Yeah, because it's including B, so you should add this. It's B plus 0.5, starting when you approximate it. So it's starting from this line, but it does not including A. Oh, sorry, I should extend it to here. Okay, it does not including A. So the boundary is here. It's A plus 0.5. So it is from A plus 0.5 up to B plus 0.5. All right. All right. So this is how you got. All right. So it's only a little bit complication when it is less or equal to C. So the boundary, so the lower bound is supposed to be 0. So for 0, remember this is binomial, discrete. Start from 0 up to n. So this one, when I convert it, I have to take a little bit more, including minus half. Because including 0, so extend it to below 0. So it's half of the between 0 and minus 1. So it's minus half. All right? Similarly, this one is n plus half. All right? Okay. So here's example. Approximate binomial with normal distribution. All right. So we work out approximate x follow this one. So x can be approximately follow normal with mean 100 times 0.9, and the variance is 100 times 0.9 times 0.1. All right. So this is how you get. Then, because this is including 80, so it extends to 79.5. All right? Or, sorry, I jump one step. I should write this as x greater equal to 79.5. Okay. Okay, so it's 79.5. And this one including 100. So it's go beyond 100. It's 100, between 100 and 101. So it's 100.5. So it is the same as this one. All right. Okay, it's a bit confusing. Because I'm going to work on a continuous random variable, continuous normal distribution. So I have to take into boundary. All right? It just like this. A simple one, binomial with n equal to, let's say, 2, and probability is half. So there are only three values, 0, 1, and 2. All right? 0, 1, and 2. So if I use a continuous distribution to approximate it, then x equals 0 is this area. So that's why it's between minus 0.5 and 0.5. And this one, 1.5. So for x equal to 1, it lies between between 0.5 and 1.5. If you treat it as a continuous random variable. So that's the reason behind all this correction. So I do this so that after I standardize it, it becomes like this. And it's equivalent to look for z between minus 3.5 and 3.5. All right. So the answer is 0.9995. All right. Okay. I'm sorry. I need to, although almost time, let me give you some idea about the next chapter. We are a little bit behind the schedule planned. Okay, so the next chapter is on sampling and sampling distribution. So the idea is that if we want to first of all, how to take a sample a random sample from a population and try to describe the population and how to describe the sample. So then we can talk about, right? So population and sample. Population is a collection of things. Sample is just a subset. And how to select this subset? There are many ways to do it, all right? But for statistics, we need a random sample. Then we take the sample, we study the sample, and try to draw inference about the population. All right. So I look at this one, but I want to get some idea about the population. Then, because I can select one sample, I can select another one, a third one, a fourth one, and so on. So I have a bunch of them. So if I put all this together, all possible samples together, then I have a distribution. I have a way to describe all this. Okay, sorry. For each sample, I compute something. All right. That, for example, I compute a sample mean. Each sample, I compute a sample mean. So I have many, many sample means. So my question is, how are all these sample means behave? How do all this behave? So that is explained by something called sampling distribution. That means this sample mean, how it behaves. So it's described by a distribution. How a random variable behaves, we describe it by a distribution. All right. So sampling distribution for sample mean, and central limit theorem. You heard it before, you used it before, so now we come to see this again. And then we talk about sampling distribution between the two sample means. And also we talk about chi-square distribution, because we want to study how S square behaves. S square is the sample variance. All right. And we talk about T distribution and F distribution. So the story is like this. So we have a population, there's many things about it. So this one can be described by a distribution. Can be a probability function, probability density function. And then we take samples, all right, represent by x1 up to xn. We can calculate some functions of this sample. For example, x bar. X bar is just the average of all these x1 up to xn, or sample variance, or the maximum of all this. So basically, these are functions of x1 up to xn. All right? Then, how they behave. Then we just consider we can take many samples. Each one I calculate x bar. Then I can plot the histogram. So that will tell me something about how this x bar behaves. It depends on the underlying distribution. So this one is x bar. All right? Then it's something about x bar. The central limit theorem is something about the distribution of x bar. Then x1 bar minus x2 bar from two samples. I mean, two population. Each population, I take a sample. So let me repeat. For this case, I have two populations, population 1 and population 2. Each one I take a sample. I call it x1 up to xn1, y1 up to yn1. I can compute x bar and y bar. So I'm looking at how the difference of this behaves, these two means behaves. So that is what we say here. Then of course, then we talk about how this S squared, the sample variance, behaves. So that involves something called a chi-square distribution. Then of course, finally, I can have sample variance from this population. All right, calculate the sample variance. I think from this sample, I also calculate the sample variance. So it's Sx squared minus S, we look at not difference, but the ratio. We look at the ratio. The ratio, how does it behave? So it's called it can be described by something called F distribution. All right. So next week we start talking about this one, and we have to do a little bit catch up. So we'll be faster and start 1 or 2 minutes earlier than usual. And 5 minutes later than the usual. All right. Okay, then I think I stop here.